Hello and welcome. My name is Carlos Osorio. I'm a MathWorks application engineer based in Natick, Massachusetts. And today we're going to talk about modeling and simulation of photovoltaic power inverters. So first, let me start by taking a look at the agenda. We're going to cover basically three topics. So first, we're going to start with modeling components such as PV cells or panels or combining them into arrays. And also we're going to look at the power electronic converters and power electronic inverters. In the second section, we're going to talk about designing control algorithms for those power electronics. We'll look a little bit at voltage and current regulation, and we're going to focus on maximum power point tracking, which is very important for photovoltaic systems. And finally, on the last section, we're going to talk about connecting these systems to the utility grid. So we're going to look a little bit at reactive power management, and we'll do throughout some transient and harmonic analysis. So most of you must be familiar with this kind of systems, but just in case, this is a very brief description. Essentially, you have sun hitting photovoltaic panels. Photovoltaic panels convert the sunlight into electricity, mainly DC power. This DC power has to be converted into AC power through some kind of power inverter. And this AC power can be distributed either to residential or commercial loads, or can be actually connected to the utility grid. In some cases, especially for standalone systems, the systems include battery storage. So this DC power is actually fed into a battery as a charger, and then the grid is powered from the battery. So let me go into Simulink. What you're seeing here is a full system model implemented in Simulink. There's four main components that I want you to pay attention to. First, we have our photovoltaic array over here. We have a DC-DC buck converter receiving the power from the array. DC-AC inverter, which is converting the DC power into three-phase AC power. And finally, that is being connected to a model of the utility grid. On our side, we're not controlling the grid. We're just controlling our system here. On our side, we have two controllers, a controller for the DC-DC converter and a controller for the DC-AC inverter. Throughout the seminar, we're going to discuss in detail each one of these components. But for now, I just wanted to make a quick run of the simulation. I am running just a 1-second simulation. And let me see if we can take a look at some of these things. So I am monitoring the behavior of the DC bus. I have two signals here. The yellow line corresponds to the photovoltaic array. The magenta line corresponds to the outputs of the buck converter. So I see the voltages, the currents, and finally the power. Notice that the power right now is about 2000 watts, which is the maximum power associated with an input irradiance of 800 watts. So in this test, I am keeping the irradiance constant at 800. If I take a look at the AC side, this is first the output of the inverter. So as you can see, it's producing three-phase AC. Actually, I can zoom in a little bit so we can take a look at this. So there's your three-phase AC voltage and your three-phase AC current. And this is the power output of the inverter. The yellow line represents the active power out of the inverter, and the magenta line represents the reactive power out of the inverter. And finally, I can take a look at the grid. Same thing. So I have the ABC voltages and currents for the grid, and the active power for the grid, and the reactive power for the grid. So as I mentioned, we're going to come back to this model, but let me focus to begin with on the first component, which will be this photovoltaic array. So first, let me close this model, and let me go back to my slides. So we're going to talk about modeling. And to begin with, MATLAB and Simulink have many, many ways of modeling devices or components or modeling complex systems. I am showing right now a mathematical model based on a Simulink implementation of a photovoltaic cell. What you're seeing here is the basic equation that you can find in most documentation. This is a single diode implementation, if I'm not mistaken. And using fundamental mathematical blocks from the Simulink library, I have built this algebraic relationship. But Simulink has advanced libraries. So what I'm going to show you now is one of our advanced products. It's an add-on to Simulink. This tool is called Simscape. Simscape is the base for our physical modeling tools. And as you can see, Simscape has electrical components. So you can model electrical circuits with actual electrical components. Instead of having to deal with the mathematics, you just build the electrical circuit and the model becomes an equivalent system to what you would do with mathematics. Or going one step further, to our advanced components library, I am showing the product I'm showing is called SimElectronics. SimElectronics in its sources library has already a photovoltaic cell implemented. So in this case, all you would need to do is grab a block from the library, and there you go. You have your cell implemented. So let me go to another example. I'm going to open my script here. Let me open a model. Here, what you're seeing is another Simulink model where I have a photovoltaic array connected to a variable resistor. The reason I'm doing this is because I want to exercise the array through a variety of values of resistance. If you notice, what I'm doing is the resistance is going to be changing linearly. It's going to be going from 0 to 30, if I'm not mistaken. And if I go inside this block, what you see is the implementation of a 36 cell series string. I have 6 orange blocks. All of them are connected in series. And here's where the graphical nature of Simulink becomes a significant advantage. You can create a single block and start copy and pasting very easily. If I go inside one of these blocks, what you will see is each one of these orange blocks has 6 photovoltaic cells connected in series. So I have a total of 6 times 6, 36 cells. This is using that SimElectronics block. Let me double click on it. So what you're seeing here is the parameterization table for that photovoltaic cell. Notice that this block has multiple parameterizations, so you can use a single diode model or an 8-parameter model, which is a double diode model. Actually, this block also includes the temperature behavior of the device, so you can model the temperature effects. And by the way, every Simulink block has a help button. If you click on that help button, it will take you to that documentation corresponding to that particular block. There's an explanation of what the block does. And if you notice here, there is that double diode implementation. I have used just a single diode implementation for my mathematical model over there. But here's the basic equation, and there's an explanation of how the temperature dependency is modeled. And there's also even examples at the bottom, probably. Let me just close this, close that. So this simulation model, when I press play, what you're going to see it is run a single simulation in where on this side, on this scope, what we're seeing is the response of that photovoltaic array. So I'm looking at the current, the voltage, and the power of the array. So I'm starting with a resistor of 0. So the circuit is short-circuited. So I am getting as an output the short-circuit current. And as the resistor increases, I am going to what is called an open circuit condition. So the voltage ends up in its open circuit value. As you see, as we're changing the resistor, the current and the voltage both are changing, which makes the power, in this case is DC, so the power will be voltage times current. The power has this behavior. And you can clearly notice that there's a peak here that occurs at a particular voltage and a particular current. What I have here associated to this model are a couple of XY plots, a couple of XY scopes. The first one is my VI scope. I'm looking at a very standard photovoltaic VI curve. And here I am looking at a VP curve, or the power curve. And this is what I was pointing out. This point here is what is called the maximum power point for a photovoltaic array. This occurs at the knee of this curve. So the whole trick here consists in keeping the array operating on or as close as possible to this peak power. That way we will be extracting the maximum efficiency out of this array. One of the powerful things of Simulink is not just the fact that you can make a model like this, it's also that you can associate it with MATLAB scripts. Simulink lives on top of MATLAB. So what I have here is this button here, when I double click on it, is going to run a MATLAB script. It's opening a MATLAB plot, as you can see. And what is happening is, if you notice underneath, the simulation is going to be running many, many times. So this is running many, many times. So what is happening is my script is using my simulation model inside a for loop, where I can actually do very quickly parameter variations, for example. So what I have done, and let's look at the results here, is I have used multiple values for the irradiance and multiple values for the temperature. So in essence, I have run 25 simulations where I have tried multiple parameter changes. What you see is the behavior. Let me open this up a little bit. What you see is the standard behavior of a photovoltaic array. As you increase the irradiance, you increase the amount of light, the power output increases. As you increase the temperature, the power output actually decreases. So this is a trade-off combination that people have to be aware of. The more light that hits your array, the more power it is going to produce, but the more power means more current is going to heat up faster, so the performance is going to be degraded. So the trick here is going to be balancing these two things. Balancing those two things, and also actually making sure that we're operating at this particular peak point for each amount of irradiance. And notice that voltage, the voltage at which this peak occurs, changes. It's not a constant. It starts at 16.7 here and ends up at 18.1. Certainly doesn't change too much, but it is some kind of nonlinear exponential curve here that makes the variation of that operating voltage. So let me go back to the slides. Let me close this. And so in order to model things using fundamental approaches, you can use Simulink to do the basic mathematics, or you can use any of our advanced physical modeling libraries. This is the collection of the physical model, the complete collection of our physical modeling libraries. The base of them is Simscape. Simscape is a required product for any of the others, except in power systems for now. What I have just shown you is a little bit of SimElectronics, where I'm using that photovoltaic cell out of the SimElectronics library directly. And when we get to our system level models, the product I'm going to be showing most of the time is this SimPower Systems product. So we have two electrical modeling tools. One models at the micro level, very detailed level simulations, and the other one is for power distribution systems, three-phase systems optimized for speed. So what if I don't want to model the mathematics? I have actually a panel, either outside or in a laboratory, or I have some piece of equipment and I have experimental data. As I was saying before, one of the powerful things about Simulink is the fact that it lives on MATLAB. So you have alternatives. If you have actual experimental data and you want to use that to create a mathematical model, we have many tools that allow you to do this. So first off, it's very easy to import your data. You can connect directly to equipment, for example, if you want, or you can gather experimental data using data acquisition, or you can import your data from databases or files. What I'm going to do in this particular case is I am going to show you a way of generating a surface fit for a set of experimental data. And from that surface fit, what I am going to do is I'm going to create an equivalent Simulink block directly without at any point building any kind of equation. So let me go back to my, let me go back to my script. And what I am going to open here is a MATLAB script. This is the standard way of programming in MATLAB. These are all just MATLAB commands. You can put them in files and you can create your own functions. And let me run section by section first. So I'm going to create a little plot here because the first thing I'm going to do is I'm going to bring in some experimental data that we have captured from a piece of equipment. So I have VI curves, same kind of curves that you saw before, only in this case they are taken from an instrument, from an actual panel. I have values for those VI curves for different irradiances. And I am going to go into one of the advanced toolboxes of MATLAB. I'm going to use the surface fitting tool in MATLAB. This is part of the curve fitting toolbox. So let me open the project here. What you're seeing is the interface, the graphical interface for the surface fitting tool. Notice that I have already preloaded my data. So here are those VI curves that you just saw on that plot. What I need to do is create a surface that maps all these points in some kind of statistically meaningful form. So this tool, this graphical interface allows me to access all the functionality from the curve fitting tool, from the surface fitting side of the curve fitting toolbox, without having to know all the functions myself. It allows me to do it interactively. So I can pick interpolations, for example, where you can do linear, cubic, biharmonic interpolations, or you can do polynomial matching, for example. You select the order of the polynomial in each one of the axes, or you can use, if you want, you can use a custom equation, which is what I'm doing in this example. Because I have a little bit of information about the shape of these curves, I know it's some kind of equation that has some kind of exponential nature, plus some kind of constant term. So in this case, what I have done is I have pre-written an equation of the form that I feel should identify these curves. So X and Y are my variables, X and Y axis, and there's a few coefficients here, A, B, M, C, and D, which I have no idea what they are. So what I'm going to do is I'm going to use all these regressive algorithms that this tool contains. And of course, I can control the options. But I'm going to do a fit here. And what this has done is it has solved that optimization problem using all these regressive algorithms. And it has given me a surface. It's giving me the statistics for my surface here, and it's giving me the coefficients that I'm looking for. That the coefficients that would actually make this map. And notice that I get the root mean square is very close to 0, and the sum of squares is also very close to 0. So that's pretty good. It's a pretty good fit. So once I am happy, I can do this many, many times with different alternatives until I find one that I like. Once I have finished this fit, any MATLAB graphical interface has, well, obviously you can save the session and you can save your data, but there's also an option called generate code. What this does is it will generate a MATLAB function that corresponds to the operations that I have done interactively. This is not a macro recording. It's actually looking at the end result and is picking up what functionality would create that end result. So this has created a default function called create surface fit. I can just save it and make it part of my collection. So next time if I have a new data set, I can bring it in and run it through this function instead of having to do the interactive clicking and pointing. So I'm not going to use this. What I'm going to do is I am going to use my own function here. It's called PVV test create. I did the same operation and I created my own function. But first of all, my system is in a pause right now. So let me go to MATLAB and let me press Okay, now I'm out of the pause. So let me go back here, and instead of running the interactive artifice, I am gonna use a function that was automatically created on that test data set. So let me just run that section. And what that is doing is it's reproducing that surface directly already on a new it could be a new data set. In this case, I only have one, so that's the one that we have to live with. Once that surface is created, now what has happened is I have an object. It will be somewhere here. There you go. There's a PVVI surface, which is a surface fit object. If I want to look at it, PV underscore VI surface. That's the object. You can look at it. There's the equation. There's the coefficients for the equation. So that is actually representative of the model. I can evaluate it at any point. It is an object, so it has multiple methods associated to it. PV underscore VI. I'm going to try to do completion. So it has, you can do prediction, you can do plotting, you can find coefficients, you can integrate, you can differentiate, you can find confidence intervals, etc. But going back to the script, what I am doing is once I have that surface, I can create a grid of irradiances and voltages, which is what I'm doing here. And then using that VI surface, I am calculating the actual current. This is being interpolated and estimated the current. So I have created a vector called array current. I'm going to use that vector of voltages and irradiances and the array current to automatically, and notice that all of these are MATLAB commands, and MATLAB commands that are actually affecting Simulink models. So I am going to create a model from MATLAB. I have automatically created a model, brought in a lookup table block from one of the Simulink libraries, and populated that lookup table block with the array current, array voltage, and irradiance values that I had calculated previously. So this block is perfectly set to be used in any kind of simulation. And I have not written any equations. Actually, if I go to my script, I have here, using that block, I have created a block that is a panel. When I double click on it, what you're seeing is the corresponding model for my Simulink electrical diagram. So I have put a couple of electrical ports from the electrical circuit. So that will be connected over here on this side. That's the electrical circuit, plus and minus. So there's going to be a loads and electronics here. This is going to be, this voltage monitor is going to check the voltage. That voltage is going to be one of the axes of the lookup table. And then there's an irradiance input, which is coming over here. This irradiance is coming in. So the value of the irradiance and the value of the voltage determine the value of the current, which is fed into the electrical circuit using one of these control current sources. So now that I did all that, I have a model, an experimental model matched to my actual panel. And this could be saved on a library, can be used multiple times. I just need to copy and paste it and connect them in series or connect them in parallel, however I want. So let me close some of this stuff. Don't save it. And I'm going to go back to the slides. So I showed you the curve fitting toolbox, which allows you to do either curve fittings or surface fittings. But on the experimental data-driven modeling side, we have many, many tools that can allow you to do this. So we have a very powerful optimization toolbox, neural network toolbox for predictive modeling, and also a system identification toolbox that can allow you to very quickly build dynamic models and transfer functions based on experimental data. So let's talk a little bit about modeling power converters now. So what I'm showing here is the idea and the main workflow procedure in Simulink is you start creating your own components. Certainly our libraries might not have all the different components that you might need, but you can start creating your own components. And once you create your own components, you create your own blocks, you can start storing them in your own libraries, and these libraries can be shared throughout the organization. So you're seeing here a library of DC-DC power converters. I have built a few topologies, a few very common topologies. So I have a buck converter, a boost converter, and a buck boost converter. Notice that our libraries have all the basic components, all kind of exponential diodes and nonlinear transistors or MOSFETs, IGBTs or JFETs or MOSFETs that you might need. And so you can very easily start building your own customized topologies, create those blocks, and then reuse them as many, many times as you wish. Now here, there's a very important distinction. So because we have two modeling tools, SimElectronics and SimPower systems, you have to figure out what is it that you want to do. So SimElectronics has very detailed, what we consider SPICE type level models of power electronic components. So it includes temperature effects, includes all the micro level nonlinearities, all the switching nonlinearities of the transistors. Full detailed simulation using SimElectronics. On the other hand, SimPower systems also has this low level components, but SimPower systems solves piecewise linear systems. So you can, this doesn't mean that it's doing full linear systems. It includes all the switching and harmonic and all the transients and harmonic analysis. But what it's doing is, instead of solving the nonlinearities on the switching devices, it is using a piecewise linear solution. So when the switch is open, you have one system. When the switch is closed, you have a different system, and it goes from one to the other as the simulation is progressing. So this allows you to build very fast solving electronic circuits. So let me go back to, before I get into maximum PowerPoint, let me go back to MATLAB here. And what I am going to do is I am going to open my first model here. I have a PV array, which is receiving an irradiance of 1,000, and it's just connected straight to a resistor. This array, in this case, if I double click on it, notice that what I have done is I have built what I would call two panels connected in parallel in this case. I have chosen to use, well, I put a mask on this, so it has a little parameter. So you can create this mask and make your blocks look like Simulink library blocks. You can even make comments, for example. But if I look under the mask here, I have chosen to use the Simulink mathematical implementation. Okay? This is just using that standard single diode equation that I showed at the beginning. Is doing the mathematics to implement this equation. The current is being fed to the circuit, and the voltage is being measured as feedback. So that solves this this algebraic equation as the simulation is going to be running. And notice that in order to make it 360 cells in series, I could connect 360 of these blocks in series. But this parametrization allows me to very easily, if you notice the mask, all I am doing to convert this single cell into 300 cells in series is I'm multiplying by 360 the corresponding parameters, and that makes my block be now 360 cells in series. Of course, I don't have the detail level of control over what's going on between each one of the cells. Based on whatever it is that you need, you can build blocks of 20 cells or 30 cells of 300 cells and connect them in series in between. That way you can control independently how much irradiance you send into each one. In this case, I have chosen just to make one single group, actually two groups in parallel, and both of them are receiving the same amount of light. My base parameters for my array in this case are my open circuit voltage is 230 volts for the 360 cells. 7 amps. The maximum power at 1,000 watts is 1,000 watts per meter squared is 1,244 watts. So what happens when you connect an array with a resistor, what is going to happen is the voltage and the current are going to try to balance. So I can run this, and you can see that for this particular value of a resistor, in this case, the resistor is 5 ohms. For 5 ohms, I'm getting a current that is about 14 amps. 14 amps times 5 volts gives me about 70 volts. That is fixed. There's no way I can change it. And what is happening is my array is producing 1,000 watts. If I actually change the resistor, make it 10, for example, and run it again, you see now the balance occurs at a different point on those VI curves, and now the power goes up. So what happens is I'm not going to be there's no way I can be assured that I'm going to have the right resistance that makes the power be the maximum for whatever the amount of light I have. So here's where we need the power electronics to do something about this. We need to put some kind of power electronic device in between. Some kind of power electronic device in between. And by the way, I already calculated just for reference. So my array, the maximum power is 2488. Is 2 of those panels in parallel, so that's why the power is twice. At 1,000 watts, 800 watts, I did the calculation, it comes out to 1964 watts, and at 600 watts, it comes 1445 watts, just for reference. But here, once I put a power electronic device in between, if I press play here, what you're seeing is, based on whatever my load conditions are, I am seeing a certain amount of power. So notice that at 1,000, I am putting out, whatever the resistor is, I am putting out 2,500 watts, which is that maximum power. And so I am paying that the maximum power. But that is because I have already picked the duty cycle for this device in such a way that it brings the maximum power out. If I change that duty cycle, let's say if I lower that duty cycle, my converter is going to be putting out a different voltage, and let's see what happens. See, the power just went down. If I keep on going down, if I make 0.4 here, for example, play, now the power, so what is happening is I am on the left-hand side of that power curve. I am going down on that left-hand side of the power curve. Actually, it was 0.6 before, no? So if I go on the other direction, 0.7, notice that, again, the power went down from 2,500 to 2,000. Actually, if I put it higher, 0.8, and press play again. See, it keeps on going down. Now I am on the right-hand side of that curve. So what happens is this, obviously, you're not going to be doing this manually. You need to have some kind of controller that takes care of this. So let me go back to my slides here. So what we just saw is if we connect the PV array directly to the load, we're very rarely going to be on the MPP. Maybe at one point be on the MPP. So we need to have some kind of power converter in between. And that power converter needs to be performing what is called a maximum power point tracking. It has to track that maximum power point. The idea is you would at all times, as your device is operating, you sense the current and the voltage. You calculate the power from there and determine if you want to move up or down on the duty cycle of your converter in order to adjust the maximum power. There are many well-known algorithms used for this. Actually, I have implemented a few of them. So that's incremental conductance, but let me show you. I have a few implementations here. So let me start with, I have an implementation of a perturb and observe algorithm. Here's the algorithm flowchart. Very typical. You can see it find it in any paper. It's just increase or decreases the duty cycle based on the comparison of the power. I have implemented that using a MATLAB function, which is a standard Simulink block that allows me to bring in MATLAB code into Simulink. And this code would actually be converted into C code and compiled when it runs on the simulation. Notice that it's very simple to implement in MATLAB because it's just a couple of conditionals here. That is the perturb and observe method. Let me close that. I have an incremental conductance algorithm. Again, this is slightly more complicated and it's a more robust algorithm. Actually, I have implemented that using Stateflow, which is an add-on tool to Simulink that allows you to implement state machines and logic charts. And what you can see is you can reproduce actually even the flowchart diagram here. One of the cool things about this is when you run it, it actually has the graphical interface shows you how the logic transitions are occurring. Yeah? Let me just close that one. And let me actually implement, I have a third one, but what I'm going to do is I'm going to open this model here. Yeah, so here I have my converter and I have my controller. My controller here that is implementing the MPPT algorithm is measuring the voltage, current, and I have a reference voltage. I'm using, this algorithm is called the fractional open circuit voltage algorithm, which is based on the principle that the actual maximum power point voltage is always certainly close to a constant fraction of the open circuit voltage, which requires you to measure a reference, which is done based on an individual cell that is attached to each one of the panels that is used as a reference cell that is used to measure the open circuit voltage. I'm using, in this case, about like 82% of that open circuit voltage for my calculation. And it's what I'm trying to do is just making my actual voltage go to that maximum power point voltage. And when I run this, what you're going to see is you're seeing the step response to the response to a step change in irradiance. Actually, I'm using a signal builder block. Notice that this allows me to construct my own signals. I can construct whatever signal I want or bring in data if I want to, bring in a real irradiance change, for example. I have a trapezoidal signal that I constructed. Is going from 800 to 600 to 1000. So if I press play now, what you're seeing is the power, the yellow line, which is the power for the array, is going from 800, which is about 2000, correct? And then I'm going down to 600, which is about 1500 watts, and then up to 1000 watts, which should produce 2500 watts, which is correct. So I am paying at the maximum power. I have a circuit breaker here that I can use actually to do a instantaneous change in the load. So right now it was not activated. So let me turn it on here. So at 0.5 seconds, there's going to be an instantaneous change in the load. So let's see if I press play, you see the instantaneous change in current and in voltage. There's a little pink, there's a little spike here, but notice the yellow line, which is the power coming out of the array. At all points, it's maintained at its maximum. So notice one more detail before I move forward. There's this little symbol here, which means that I have some kind of configurable subsystem, or in this case, what I'm using is what is called a subsystem variant. So in the same model, I have multiple versions of the device. So I have an average voltage version here using average voltage converter bridge. All of this is SimPower systems. Notice that this block can be transformed from an average voltage version to a MOSFET bridge, for example, just by clicking a drop-down menu, or I can change it to an IGBT bridge if I wish, or I can go back to my average voltage. The cool thing about the average voltage versions is that it not only allows me it doesn't require a PWM high frequency switching, so I can keep my integrator in continuous time, and I don't need to implement the PWM frequency. So this model can run very fast. Not only can run very fast, but it's also linearizable. These blocks are linearizable. It's just a power equivalency. Now, of course, all of this is can be controlled by an outside MATLAB variable. Actually, I have this back mode variable. Like if I set it equal to 2, for example. Now, what is going to happen is when I update my model, Control D, now it has switched to the detail implementation. So if I look in here, now the circuit that is going to be used is, and sorry about this, let me just foreground, blah. black. Okay, this is a MOSFET implementation, 2 bridges, same converter, only now this is a realistic implementation and is using a 10 kilohertz PWM. No, this is a PWM generator block from the SimPower Systems library, 10 kilohertz. You can actually go from 1 arm to 2 arms to 3 arms to the double 3-arm bridge. So it would automatically generate the sequence of pulses for you. Of course, because I'm going to be running those high frequency pulses, what I want now is, instead of running it in continuous to make the simulation more efficient, I'm going to use a discrete integrator. I am using a 1 microsecond integration step to capture the 10 kilohertz PWM. And when I press play here, what you're going to see now is the full switching simulation of this device. So what you do is you design your device, you design your controller in average voltage, you design your controller, you can run very quickly through multiple simulations, and then once your controller is designed, you can test it against the full nonlinear switching simulation very quickly. Notice that I didn't change models. All I did is I changed the subsystem that is being used right now. So you can see the high frequency and harmonic behavior that I have in my system. But the performance is still pretty good. So there's some oscillations, and let me just stop it because you guys get the idea, I guess. If you go in, you will see all the high frequency behavior now. But it is the same simulation model. Let me just close that one. And what I'm going to do is go back to my slides. This is just an explanation of the incremental conductance algorithm. Of course, now you can, with the same bridges that I showed you, we can build and model DC to AC power inverters. And there's built-in tools that allow you to do harmonic analysis, and I show you how to do average voltage models, for example. So let me go back to MATLAB. And what I am going to do is I am going to open this model here, where I have my converter. I have my DC-DC converter, and now I have a DC-AC inverter. Same idea. I have a circuit breaker that is going to connect an additional load at some point. So this is a double implementation. Again, I have the average voltage implementation, and I have a detail implementation using an IGBT bridge. In this case, my IGBT bridge is a 3-arm bridge because I want to generate 3-phase AC. So let me I'm going to be running the average voltage first. So let me press play here. And what you will see is this is the DC side. So 2000, because I think I'm using 800 irradiance, so 2000 watts on the DC side, and then on the AC side, where's my scope? Oh, here. There's on the AC side, I am producing 3-phase sinusoidal. Let me get a little closer here. So there's your 3-phase voltage and your 3-phase current and your AC power. The yellow line is, as I said, the active power on the AC side, and the magenta line is the reactive power on the AC side. Notice very quickly here that there's a change in the magnitude, because on my controller here, I am actually putting a step change in the desired reference. So I'm going from 1 PU per unit, means like whatever capacity you decide to your system, that's like full capacity, to 0.8 at 0.5 seconds. So the first change you see is going from 1 full PU to 0.8. And then at 0.8 seconds, there's a load being connected. And that load is actually changing the so the voltage is still at 0.8, because my controller is actually now regulating voltage, and it's changing the current to compensate for the change in the load. Let me just go in here very quickly. What I have is just a standard voltage regulator, and all of these are SimPower Systems components. When you're dealing with 3-phase systems, there's a slight additional operation that you need to do. So it's hard to control the 3-phase sinusoidal. So what you do is you do a coordinate transformation. So from ABC, you move to direct and quadrature currents. So there's an ABC to DQ transformation. And then once the controller is done, then you go back from DQ to ABC. All of these blocks come with the tool. I need a sinusoidal reference signal, a modulation signal, which I am generating using one of these discrete PLLs. I'm generating a 60 hertz three-phase sinusoidal. And I have two PI controllers. One is controlling the D axis, which is the active power, and one is controlling the Q axis, which is the reactive power. Both of them are PI controllers. Notice this. What I want to do is this. Oops, not that. Sorry. These two little symbols. This one here, and this one here, which are just being defined. They're defining inputs and outputs on my system. So if you have the control design tools, you can click on any signal, and in order to do linearization or control design, you can select the signals as inputs or outputs. Notice that I'm defining one input there and one output here. So my active voltage reference is my input. My active voltage actual calculation from the system is my output. So I could change my controller. I could do control design. But before I do the control design, I want you to look at something. So first off, I'm going to need, in order to to do control design, I'm going to need to linearize this system. So I'm going to try to find some kind of decent operating condition first. So let me pick, because otherwise the transfer function is not going to exist. So let me find here, this point, like 0.037 seconds. So at that point, I have a peak on the first phase. Okay, so 0.037. Okay, so just take a note of that. And what I am going to do now is I'm going to go to Tools, Control Design, and then Compensator Design. Notice that there's linear analysis. If I just wanted to do linearization, I can do linear analysis. Select blocks. So this is going to look at my Simulink diagram. It gives me all the alternatives here. I'm looking for, in this case, the inverter controls. I have my voltage regulator, and notice how it automatically detects there's a VQ and a VD. I'm going to do the VD controller, the direct axis. I'm going to pick that block. My input and outputs have been defined in the diagram, and I'm going to pick an operating. I can write down manually whatever operating point I want, or I can calculate it, or I can use a simulation snapshot, which is what I'm going to do here. 0.037. That's the point. That's the number that we were looking for. No? And what I'm going to do is tune blocks. So notice that this is analyzing the model. It's going to run the model up to that operating condition. It's going to linearize it around that operating condition. And next is asking me what kind of plots I want to design my controller. So I can open root locus, body plots, and I can look at step responses, body responses, Nyquist plots. I'm going to just pick a step just to keep it relatively simple. So here, this is opening actually the step response of my system. And this is, so let me just put some grids on this. So this is all using the control system toolbox and Simulink control design. So this is my compensator design task. And this is my response right now. This is my step response. So notice that there's like a high overshoot right now with whatever gains I have. So I can interactively tune it. Notice that I can move it up or down. As I move it up and down, I can see how the response is changing. And I don't need it to be that fast. So I can slow it down a little bit and maybe, like maybe there. And actually you can, all this responses, you can actually look at the characteristics of the response. So I can look at, peak responses, for example, if that's what I wanted to look at. It's going to give me at what point all the information I need. And as I move this up and down, I'm going to see that value changes. So I have 10% that maybe I have a requirement that says I can accept maximum 3% overshoot. So right now I'm at 3% overshoot. So that seems safe enough. So let me, where's my compensator task here? This is my compensator editor. I'm seeing my parameter, my PI. I could actually tune them with these sliders. So it's giving me the values. I can actually store the design if I want, or directly update the Simulink model parameters. This is my compensator structure right there. So I have all the information at the tip of my fingers here. So now that I have, do you want to save the project? No. Now that I have updated my simulation model, I can actually run it again and maybe see either increased performance or it's following my, where is my, oh, I closed it, I think. I can, yeah, so I can see the response. Apparently not much change. But actually what you have to look at here is what is the harmonic behavior of this system. So in order to do that, what I'm going to do is I have been running average voltage versions. And as you can see, just so you can feel the speed of the simulation, I'm running 1 second average voltage simulation. But what I'm going to do is I'm going to go back here and I'm going to change this to, and I'm gonna do, there's an inverter mode, so I can control all of this from MATLAB, so you can actually see how you can design a script, a MATLAB script, where you run all the average versions and then change to the detailed versions afterward. So now I have my detailed buck converter and my detailed inverter here. Once again, I'm gonna go into here, change this to discrete, and it's going to run with 1 microsecond integration step. Only I'm not going to run it I'm going to run this for 0.2 seconds maybe. So now what I'm doing is I'm running my full system simulation with all the high frequency switching. I'm using a 10 kilohertz PWM frequency on the buck converter and 10 kilohertz PWM frequency on the AC inverter. I'm generating 60 hertz, 3-phase AC voltage and 3-phase AC current here. And this is the actual power of my system. Okay, and what I want to do now is once I run this, I'm saving this information because what I want to do is show you how to do harmonic analysis. I can double click on my Power GUI tool here and notice there's the configuration parameters, but there's also many other functionality here, including FFT analysis. So if I open that, you can see that you can look at the current, at the voltage or the current, and actually I can pick harmonic analysis here, harmonic order. I'm going to do display, and this is going to immediately calculate the total harmonic distortion, in this case 152, which is pretty decent. No? If you want better response, you can go again and retune your controller, or do some controller that attacks these harmonics, for example, like this 7th harmonic, or actually, if I go a little higher here, let me do like 20,000. Yeah, what you're seeing, so this is good. So what I'm seeing here is those minor harmonics are not that important. There's the harmonics of the converter. And the reason why you're seeing these harmonics is, this makes sense because I'm producing 60 hertz and I'm using a 10 kilohertz PWM frequency. So 10 kilohertz is about 166 times 60. No? So that's why you're seeing 166 harmonic and higher orders of that, like twice of that over here. No? So that's one of the reasons why some people use higher order converters. The more devices you put in, the farther up you're pushing these harmonics, this higher order harmonics, and the cleaner your overall signal is going to be. Okay, so now let me just close this. And to finish, what I want to do is I want to open the last model that I have here, which is now the whole inverter with the controls connected to the utility grid. This is a model of the utility grid. It's an idealized model of the utility grid. It's just a very high impedance power source, really, with some dynamics. I am measuring the ABCs of the voltage, current, and power for the grid side, because I'm going to look at that. And the converter for the inverter has changed. The controller for the inverter has changed. So I have my voltage regulation here. But first, before I connect it to the grid, I need to synchronize it to the grid. So I have to measure the ABC voltage on the grid. I'm passing it through a PLL phase lock loop controller, which again is an existing block from the SimPower Systems library, which is generating the synchronization wave. The synchronization frequency. Actually, you look at my controller, it looks very much the same as before, only in this case, instead of me generating my own sinusoidal wave, I'm bringing that from the measurement from the grid. And I am picking the controls for the current in this case, because what I want to do is I want to make sure that I pass the maximum amount of power into the grid. So I have a power management controller here, just an integral controller on the power, and I have an integral controller on the an integral controller on the active power and an integral controller on the reactive power. So let me just press play and run this. And what I want to look at is several things. So this is the DC side. So here, so I have the yellow and the magenta. Again, yellow is the array and magenta is the buck converter. Notice that it's staying at its maximum point. The current is changing following that. The voltage is also changing, but very little, but it's changing. That's the AC side. Then I have the inverter output, the inverter measurements. So notice I have my inverter, which is what I am doing is current control right now in my inverter. So notice how the current sort of mimics the power output, because the idea is to keep the voltage constant. I am going to be hooking this to the grid, and the grid is operating at a particular voltage. So this voltage has to be maintained constant. But that is done by the reactive power management. My active power is controlling the current. Notice the power output of my inverter, which is mimicking the DC side here, is passing through as much power as it can from the inverter. And when I look at the grid, there's my grid. Of course, it has constant voltage. The current changes. So notice that at some point the current that the grid is putting out to the load is less, because now part of the load is being fed by my system, by my inverter. And actually, if you look at the power output of the grid at that connection point, I am doing this. I'm looking at here, this connection point here, the connection to my array. So the power output at that connection point, once the system gets hooked up, it goes down. It looks, actually, if I change the scale a little bit, it would look more better. Yeah. So it looks little because the grid has a very, very high power. So it proportionally is little, but this is absorbing all the power it can from the array, from my photovoltaic array. So my array is happily providing power for this 1,000 watt load on its side. And then when it gets hooked to the grid, it cannot handle 1,000 plus this 5,000. So the grid is providing part of the power for this 5,000, and the array is compensating, is putting as much as it can to cover what it can from here. Actually, if you notice that the last plot I have here is my synchronization. So I want to just look at, no, that's not what I wanted to happen. I'm going to zoom in a little bit. So here is how the yellow line is coming from my inverter. The magenta line is coming from the array, the magenta line is coming from the grid. So notice that at first the phase voltages of the inverter and the grid are unsynchronized, but the PLL does its job and very quickly starts putting it together. Actually, let me zoom in, capture a little bit more. I mean, you can see how about like at 0.05 seconds, we are already both waves are in phase. In this case right now, the connection is occurring after 20 cycles. So about here. But this is very important, because if you hook this up, let's say if I hook it up after 2 cycles only, before it actually gets synchronized, before it's actually synchronized, and I'm going to run it again. So what you're going to see is the moment, where's my inverter? 2 cycles, yes. Let me actually exaggerate. Let me put it at 1 cycle. So let me run it again. This is one of the good things about having things on average mode, that you can run things very fast. So it's hard to see, but what is going to happen if I look at the inverter probably. Yeah, so at the moment of connection, because I am not synchronized, there is a jump in current, and well, look at the power, and there's a big giant reactive power happening here. So that is not good, because that's going to introduce all kinds of harmonics into the grid. Okay, so that is kind of, well, I showed the controls, how you can do controls, linearize your system, test and verify it. So I'm going to stop there, and I'm going to let you guys write down your questions in the Q&A panel. And hopefully we'll come back and answer them in a couple minutes. Okay? Thank you very much for listening.